The last carboxylic acid derivative that we're going to discuss is the amide, which is also related to a nitrile, and that's why we're going to include those in this video as well. The chemistry of amides is extremely important if you want to understand proteins, which are the catalysts of virtually all biochemical reactions. They're composed of consecutive amide bonds through long chains. So anyway, we're going to talk about how can you form amides and how can you react amides, which is going to be really important later on for understanding protein structure, function, and synthesis and degradation as you move on in your studies. So in a simple sense, remember that amides are the least reactive carboxylic acid derivative, which is kind of nice because we're very limited in the kinds of reactions they can undergo. We can't make esters or acid anhydrides or acid chlorides from amides. Pretty much the only thing that we can do with amides is make them and then use them to make carboxylic acids. So remember, how do we make amides? One way you can make an amide is take an acid chloride or an anhydride, react it with an amine. You need one equivalent as a nucleophile and one equivalent as a base to get your amide. So that's pretty much how you make amides. That's all you really need to know. What kind of reactions do they undergo? Well, they undergo hydrolysis under acidic and basic conditions. Acidic hydrolysis is treatment of an amide with acidic water and strong heat leads to carboxylic acid plus the ammonium ion. What's the mechanism for this reaction? It's going to be very similar to what we saw for esters, right? Let's say we have this amide. We react it with water and acid. So hydronium ion is going to be the source of protons, right? Water is going to be our nucleophile. It's not a good enough nucleophile to attack an amide by itself. Amides are not very electrophilic. They're the least reactive. So we must protonate this oxygen first to make this carbon more electrophilic. Now everybody's happy. Now water can come along, which is present in a large excess, and attack the carbon, break our carbon-oxygen double bond to give our classic tetrahedral intermediate, right? And then transfer of that proton back to water to regenerate our hydronium ion is going to give us this tetrahedral intermediate with an OH and an OH and an NH2, right? We're hydrolyzing the amide, so the NH2 is going away. And the trick that we keep seeing over and over again is if you want to get rid of something, protonate it to turn it into a better leaving group. So we're going to use this source of protons that we have to protonate the NH2 to make it into ammonia, which is a good leaving group. It would be neutral if it left NH3 plus. Now what can happen is we can reform our carbon-oxygen double bond and our ammonia can leave, which gives us a protonated carboxylic acid, and transfer that proton. Remember, the solvent is always going to accept the proton, so transfer that proton to our solvent molecule, gives us our carboxylic acid. This is hydrolysis under acidic conditions. Remember, under acidic conditions, you can't generate any negative charges, right? So we have a positive charge here, positive charge here, positive charge. Everything's neutral except for our reagent, right? Positive charge is propagated throughout the whole mechanism. Nowhere do we have a negative charge. You never want to generate hydroxide under acidic conditions. You never want to generate any O minuses. We can also do a basic hydrolysis of an amide, right? Initially, what we're going to get after step 1 is a carboxylate anion. This is very similar to basic hydrolysis of an ester. And then this second step just protonates that to give us the carboxylic acid that we want. And the mechanism for this, again, is not going to be hopefully too surprising, right? We have hydroxide, which is sufficiently nucleophilic that it could attack the carbon straight away without any previous activation. We already had a negative charge on oxygen, so it's okay to generate the negative charge on oxygen at this point, right? And now, reformation of the carbon-oxygen double bond and kicking out of the NH2 minus ion, while unfavorable, is driven towards product, because even though you're generating this high energy intermediate, the product is rapidly deprotonated by more hydroxide that's present in solution in an irreversible acid-base reaction. It gives us an O minus ion, right, which is the result of step 1, and then protonation with the hydronium ion, which is a separate step. So now it's okay to have a positive charge here. We added a second step. We added a second reaction to protonate that oxygen to give us our carboxylic acid. This is basic hydrolysis of an amide. And those are really the only two reactions of amides that you're going to need to know, which is kind of nice. In terms of nucleophiles, the other nucleophiles that we can look at are lithium aluminum hydride, which can reduce the amide to the amine, right? We have nucleophilic hydrides, which can add to the carbon. And eventually what's going to happen is we're going to introduce these two hydrides by lithium aluminum hydride to give a primary amine. I'm not really going to worry about you learning this mechanism or knowing it unless you want to. Remember, you can make nitriles by SN2 reactions. So now we know lots of ways. And we said you can make nitriles into carboxylic acids through acidic hydrolysis in a previous video. We just didn't introduce the mechanism. So now what we're going to do is talk about reactions that nitriles undergo, right? You can take a nitrile, and under acidic conditions that hydrolyzes to an amide, and we just said amides hydrolyze under acidic conditions to carboxylic acids. You usually don't stop at the amide stage. Similarly, you can hydrolyze a nitrile under basic conditions. Initially you get the same amide, which then undergoes hydrolysis to a carboxylate, which then gets protonated in a final step. So quickly, I'd like to go through those mechanisms, and then we'll wrap up this video. So if you're under acidic conditions, right, and you have a nitrile, just like if you have a carbon-oxygen double bond or carbon-nitrogen double bond, water is your nucleophile, but to induce nucleophilic attack, we need to activate this carbon. We need to make it more electrophilic, so the first step is going to be protonation under acidic conditions. So now, this carbon is a good electrophile, and so water is going to be our nucleophile in this step. Attack the carbon, break the carbon-nitrogen triple bond. So what do we have here? We have this double bond became a lone pair on nitrogen. We have water attacked. We have a positive charge on the oxygen that we need to get rid of. That's going to get accepted by another water molecule to give us this neutral species. Whoops. Now what we can do is protonate the nitrogen under our acidic conditions, right? We can protonate our nitrogen. Now what we have, something like this, which has a resonance structure that places a positive charge on our oxygen, and loss of a proton to water, to our solvent, gives us this, which is an amide. And we just talked about hydrolysis of amides under acidic conditions. This is the same as this, which can continue to undergo hydrolysis reactions until you get a carboxylic acid. So this can continue to react under the previous mentioned mechanism to give a carboxylic acid. That's the acidic mechanism. The basic mechanism, hopefully there's not going to be any surprises here. We have a carbon-nitrogen triple bond. Now we have hydroxide. which attacks our carbon-nitrogen triple bond. To break it right straight away, we get a negative charge on nitrogen and an OH, right? In the presence of water, which is our source of protons in this case, we protonate the nitrogen to give this guy. Now this guy can undergo deprotonation under our basic conditions with our hydroxide, which gives us this thing. Which has a resonance structure that looks like this. Which can then pick up hydrogen from water. Now we're back at our amide. And remember, if we just rotate around this bond, we have an amide. These can get hydrolyzed. They can continue to react to give carboxylic acids under basic conditions, as we just discussed. Other things that can happen with nitriles, which are kind of interesting, Grignard reagents give ketones in this case. If we have a nitrile, that's going to react with a single equivalent of Grignard reagent. Let's say we have a methyl here. That attacks our carbon, right? So what do we get? We get a carbon-nitrogen double bond with a negative charge and a methyl here. And that just sits there because this nitrogen can't get protonated in order to get activated towards nucleophilic attack. And then if we add acid, what do we form? Well, initially we form an imine, and we already know that imines hydrolyze to ketones under these acidic conditions. The last thing to talk about is that we can reduce nitriles with lithium aluminum hydride to give primary amines, just like we can with amides. Okay, to summarize, amides can be made from acid chlorides and amines. We know that they can form carboxylic acids under acidic or basic conditions, and we know that they can be reduced to primary amines with lithium aluminum hydride. Similarly, let's talk about nitriles for a second. They can be formed by SN2 reactions. They can be hydrolyzed to carboxylic acids under acidic or basic conditions. They can react with Grignard reagents to make ketones, and they can react with hydride reagents to make primary amines.